First, let me introduce myself. My name is Mike, and I work at LinkedIn, where two things I do make me a great person to talk to you about TypeScript. Number one, I run the developer training program. So I am a workshop instructor for the company where I help, level up all of the engineers there in a various array of topics, including TypeScript. And number two, I am a tech lead on the front end stack where I predominantly focus on TypeScript adoption, right? On making it so that if teams wish to use TypeScript with their project, everything works smoothly and the documentation tools work and all of the linting works nicely. So I have been knee-deep in this area, and I'm so happy to be here to share a lot of what I've learned with you. So first, before we jump in, and we're going to get our hands dirty really quickly here within about 10 minutes, but let's first pin down exactly what TypeScript is so we know what to expect. So it's an open source programming language. Primarily it's maintained by a core team of developers at Microsoft, and it's a typed syntactic superset of JavaScript. What that means is if you take TypeScript's syntax, you can kind of see JavaScript's syntax within it. It does not mean that every JavaScript program can happily run through the TypeScript compiler without any errors. So there's sometimes confusion about that. Now, it's true that if you loosen up the TypeScript compiler and kind of set it in the most flexible possible mode, a lot of regular JavaScript programs can make it happy. But there are inherently things you can do with a really flexible, dynamically typed language like JavaScript that will never make a strongly typed language happy. TypeScript compiles to readable JavaScript, and it has no runtime part, no runtime component. What that means to you is the types disappear in a build step. So you're just really, you can almost think of it like a static analysis tool that does a lot of checking on your code base. But when you have that build that you're sending to your users or that you're running in Node.js, unless you do some really exotic backflips, none of that type checking is there. And that's good in some ways and that's bad in other ways. It's good in that there's no cost at runtime, right? It's not going to slow your app down. Runtime type checking, that's extra code that every user in every browser is going to be running. So TypeScript disappearing in a build step is good there. But of course, when you're receiving some data from a fetch or you're getting some input from a user, it's important to understand that there's really no type checking that's going to happen there because at that point, it's just a JavaScript program. So the project kind of has three things inside of it. There's the programming language itself. There's the language server, which is a program that kind of feeds your text editor a lot of great information that can manifest itself in autocompletes and tooltips as you hover over various things. The language server is sort of something that you can query about what's going on with my program at this point. And then there's the compiler, and that is used by the language server, but it is what actually performs the type checking, and it is one way of taking TypeScript files and emitting JavaScript files. A huge advancement that came along with Babel 7, and Babel is what lets us take modern JavaScript and kind of boil it down so that Internet Explorer can run it, and so you can just simply state which browsers you care about and you get something compatible. Babel can now take TypeScript files as inputs. Now, it's important to understand that no type checking is involved there. Babel kind of just knows which parts of the TypeScript code it can eat and ignore, leaving only the JavaScript behind. So you definitely want to use the TypeScript compiler side by side with Babel, but the important advancement there is you have one piece of tooling that's responsible for creating your JS files. You don't have to worry about how does TypeScript represent a class for Internet Explorer? How does Babel represent it? And is there going to be a collision there? So you can have a great assurance of consistency. And almost think of the TypeScript compiler as a really fancy linter or another static analysis tool that just kind of verifies that everything looks good, but doesn't actually produce output. So since I taught the last version of this course for Front-End Masters, which was in 2017, we've seen a 300% increase in downloads. And we can see, like this is a monthly download graph on the bottom. We can see that it's basically matched React in terms of popularity and prevalence of use. So NPM does a survey every year, and they ask their respondents what flavor of a JavaScripty language do you use, like CoffeeScript, or do you use ES6 or ES5 or TypeScript? And it turns out 46% of respondents said that in some part or another of their programming, they make use of TypeScript. And if you look at all of the packages in NPM, over 40% of them declare TypeScript as a dependency or dev dependency. So you're probably using it, even if you don't think you're using it. You're using something that's written in this typed language, and depending on that type checking. And potentially, you could take advantage of that type information. So why would we want to add types? Why would someone bother to make this project? First, it gives us the opportunity to take assumptions and constraints we have as authors when we write a piece of code. It gives us an opportunity to make those a part of our code. So if you have a function that's designed to take a string as an argument, you actually have a place where you could say, this argument must be a string. Now, if we were just looking at regular JavaScript, you could write a comment saying, please only pass a string to this function. But you'd be relying on people reading your source code and finding that. You could assert that it's a string, like within the function, throw an error if the type of this value is not a string. But that starts to add up. It starts to get towards something we would call defensive programming, which is where you basically don't trust any of your inputs. And it introduces a lot of overhead and complexity, both like performance overhead and cognitive overhead, right? You hire a new person to your team, and they're going to have to weed through this stuff and figure out where are the assertions and like what's this function actually doing after it's satisfied that the data is correct. Makes things a little difficult to maintain. So this types assist us in taking all of our developer intent and making it, like encoding it into the code we write. Types help us catch common mistakes, like a spelling error. I make spelling errors a few times a day, at least leading up to my second or third cup of coffee. Spelling errors are very common. So because there's a validation that you're only accessing the properties that you should be accessing and that you're naming your arguments correctly, you're less likely to make those with types because you've defined what should be accessed and what everything else you should not be trying to touch. An incomplete refactor is another good example. Imagine you have a function that you're using in 4 places and you add another required argument and you only update 3 of the call sites, leaving one out of date. The compiler will let you know that there is a mismatch here. So it helps catch that kind of thing, which is very difficult to catch in JavaScript. You'll see throughout our work today that we're moving a lot of errors we would find at runtime up to compile time. So we're getting earlier feedback. And we're getting feedback as a result of static analysis, which is an analysis that just looks at your source code and comes to conclusions, as opposed to runtime analysis, which requires you to actually go through and execute every path of your code. So you could catch some of this stuff with tests, absolutely. But while you're writing your code, and maybe you haven't written your tests yet, or maybe your tests are incomplete, has anyone here worked on a project that has an imperfect test suite? I have. All hands should go up right now. All of your test suites are probably imperfect. So This means you're not depending on tests to catch this type of error. You certainly can make other types of errors. And then finally, right away, you're going to see that TypeScript is the foundation of a great developer experience. It's something that the JavaScript ecosystem has kind of been missing relative to typed programming languages. So I started out as a Java developer, and I used a wide range of IDEs to write my code in, and I got a lot of outlines showing me like these are the classes and these are the members of the classes and these are public and these are private, and I got great autocompletes because the language was set up in such a way that you could know what you're supposed to be accessing and what you're not, and what is the value of the thing you're accessing. This is much harder to figure out in a dynamically typed language like JavaScript or Ruby. So here's a rough outline of what we're going to learn. We're going to start out with kind of a crash course in the TypeScript programming language. Now, we don't have time, and it's not a good use of our time, to go through every little facet of what can be done with TypeScript. My main goal here is to ensure that I leave you with a great mental model of how to think about this programming language, because then you can go and you can learn about all the little corners that I may have left untouched, on your own. We'll learn about configuring the TypeScript compiler. This is important because it can be the difference between shrinking your code by 70%, right? Like if you're building for IE6, there's a lot of extra code there because we can't really depend on as much being there in the browser for us to use. And it also helps you set your strictness settings. So if you really want type safety, you kind of have to set things appropriately so the rules are strong, right? We will go through a 3-step practical strategy for converting from TypeScript to JavaScript. There are bad ways to do this. If done correctly, and if done the way that I'm going to teach you, it can be a very smooth, incremental process. It doesn't have to be a big disruptive thing, right? We don't have to treat it like we're rewriting, a JavaScript program in Swift or something completely unrelated. We can take advantage of the similarity between these languages and the ability for mixing JavaScript and TypeScript modules. We'll focus quite a bit on advanced types and generics. And you can think of generics as parameterized types, right? We pass a value to a function to sort of parameterize a value. We can pass type parameters to generics to parameterize types, like a fill-in-the-blank kind of situation. And at the end, I want to give you a quick demo of how the TypeScript compiler looks at your code. So we're going to use the JavaScript API for the TypeScript compiler, not because I think a lot of you will end up using this in your apps, but it allows us to peek under the hood and to see how TypeScript understands our code and how it sort of splits it apart and how it represents it in data structures. That's really important in order to validate that you have the correct mental model. If you've checked out the project, which is bit.ly/fem-ts for TypeScript, we can open up the examples folder and go to a little sub-project in there called Hello TS. And we're going to learn about how to use the TypeScript compiler to turn TypeScript into JavaScript. So I'm just going to open up, in Hello TS, we've got a source folder, and then index.ts within that folder. There's just only one file in that folder. What we've got here is some TypeScript code. And it's just 2 functions and then a tiny little program that runs, that uses the above functions. First, we have a function that returns a promise that resolves after a set period of time. So you can think of this almost, it's the responsible equivalent of a sleep or a wait, right? Where we pause execution and JavaScript's free to go and do other things while we're waiting, and then it'll resume after a specified number of milliseconds. It's just wrapping set timeout and then resolving the promise. This second function, it adds two numbers together, and we begin by waiting half a second before we return the result. So it's a really slow calculator, basically, that can only do addition of two numbers. Not incredibly useful. I've chosen this because it includes some modern syntax that some browsers and JavaScript environments we may care about, they can't understand natively. So we're going to look at different ways of compiling this so that we can get an output that will run where we need it to work. All right, I'm going to open up my terminal here. So, and just to be clear, it's important you use Visual Studio Code for this workshop. It is the editor that is built kind of hand in hand with TypeScript, right next to the team that builds TypeScript itself. So it's possible to set up other environments such that you get the kind of experience we're about to see, but it requires much more effort than what you'll see right here. All right, so the first thing I'm going to do, I'm going to go into examples, hello TS, so I'm sort of working in the hello TS folder. And I'm going to see what's in the source folder, only this one file. So I'm going to use this command, tsc, which is TypeScript compiler, source index ts. And what we have here is another file that's popped up in Next.js. And if we look at these side by side, it's a lot of extra code. I mean, if we try to find our original code, it looks like it starts down here, and then more kind of explosion of complexity. What we're seeing here is ES3 JavaScript, the kind of JavaScript you would run in Internet Explorer 6. So we probably don't care about Internet Explorer 6, but this is the default. By default, you build JavaScript that can run basically anywhere. We can compile it again with a flag that will indicate that things don't need to be dumbed down quite so much. Target ES 2015. Okay, well I can see right away, like a lot of the code went away. Line 31 is where we end. And we still have a little overhead here, like some helper code that's necessary for compatibility reasons. But now I'm seeing promise pop up. Promise is a part of ES6 or ES 2015. I don't see that we have await. So it seems that async and await are not something that is available with this version of JavaScript. So we can go up to ES 2017 and we should see await come back. And in fact it does. There's our async and our await. All that's really changed, if we look at add numbers, is these little extra bits of information, which I'm sure you can assume that that means like A should be a number and B should be a number. That has disappeared because that's not part of JavaScript. But other than that, I mean, we have, close as makes no difference, the same number of lines of code, right? Now, if we tried to run this, let's try to run this in Node because there's nothing here that's necessarily browser specific in terms of like functions we're calling. So we could just run node source index.js and we'll get an error. And that error says unexpected token export. Has anyone here worked with Node before? What am I running into here? Can you spot a problem that would make Node potentially unhappy? Export. Can we maybe look? How does Node.js export things? Module.exports. Right, and this is because common JS modules are used for Node. We import things with require. We export things with module.exports. So we can add another compiler flag here. modules, or module, common.js. And we should see this change. And in fact, it does. Exports.addNumbers. And now if we were to try to run it, everything works, right? We wait for a brief period of time, and then we log out the result of adding 3 and 4 together. So there are a lot of different flags you can use here. Here's another one of my favorites, --watch, and that will leave the TypeScript compiler watching the source files so that if I were to change something, like let's say I add a string here, result is, and comma, and I'm going to hit save, and you can see the file on the right kind of updated automatically. So it watches your source files and will incrementally update only what's changed. It's a nice, fast, incremental compilation. It doesn't do your whole app, just what's changed. So these commands are going to get kind of big and cumbersome. The conventional way to do this is to use a configuration file instead. So in my source folder, I'm going to create a file, in the hello TS folder, I'm going to create a file called tsconfig.json. And we're going to look at the various things you can do here to set it up. There are 2 things you need to think about when configuring the compiler. Number 1 is defining which files are the inputs. And you can do that either by specifying a list of files, or my preference is include, which lets you specify some globs. You've seen globs before, like star.ts or something. One valid glob is everything in the source folder, right? So that's number 1. What are we compiling? The second option is, how are we compiling it? What are the compiler options? So to get an equivalent result of what we were just looking at, we would do module, common.js, target, and VS Code gives you some, there's a JSON schema behind this file that'll give you the allowed values for this. So we'll pick ES 2017. And just for fun, I'm actually going to put the output in a different directory, put it in the lib folder. And this would make it really easy to publish only the compiled output. If this were a library, I'd want to publish that to NPM so that JavaScript and TypeScript consumers alike can import my code. They don't have to be able to read TS files. So now I can just run tsc. Everything looks good. And I should, after refreshing here, have a lib folder with this index.js in it. Now, so this is great. So I could almost like think of it as, if I delete our first attempt here, I could think of us like our source folder has a TS file, our lib folder has the JS output. I could check the source folder into Git, and I could only publish the lib folder because we really only care about the compiled output. And you'd keep things very well organized in that way. So this is great. One problem I see, though, we have all this great type information, and the stuff that I would ask my users to run is missing this type information. Now, it's necessary for me to provide an option to not use type information because people might write JavaScript apps that depend on this code. But I want to make sure I provide some other stuff on top of that. So we're going to say declaration true and source map true. Run the compiler again, and we should see some new files pop up in the lib folder. One of them is a .d.ts file, right? Same file name, but it's .d.ts instead of .js. And this, if you look at it, it looks kind of like a function with no implementation. We can see that the names of my arguments are there. We can see that we have types for the arguments. This we'll learn in a moment, but it happens to be the way you represent the return type of the function. But nothing in here describes like how you would actually add A and B together. And nothing describes that we're waiting half a second before returning that. So this is a type declaration file that is meant to layer right on top of the JavaScript that it represents. And if you're using a TypeScript-aware editor like VS Code, it's going to read this and kind of match it with that JavaScript and understand that these are the types that are meant to go along with this code, which is is what is run in order to get the value we're after. The other file is a source map, right? So this is what would let us, if you put breakpoints in your code, it's what would, in your debugger, map that breakpoint back to the original TypeScript source. So you kind of feel as if you're debugging through TypeScript code, when in fact that is not what's running. What's running is the JavaScript. I can close by giving you another example config here. So this is a more complicated one. The compiler has native support for React, so it can parse JSX. You can understand that, like if you call your files TSX, that's like a TypeScript React file, but you don't need anything other than the TypeScript compiler in order to check that. Setting strict to true is really important. You may want to have strict as false, its default, as you're sort of moving from JavaScript to TypeScript. The approach I'll show you involves starting with a loose configuration and then tightening it up. But ultimately, you want to end up in a place where you've got some of these strict features turned on. Forbidding implicit any, that's also important. Implicit any's are like wildcards. They're places where the compiler couldn't figure things out by itself, and it's kind of a place where any type is allowed. And to put that in a more pessimistic way, it's a place where you have no type safety, right? The TypeScript compiler can check and compile regular JavaScript. And if you're interested in learning more about this, check out the Visual Studio Code course on Front-End Masters. You can use JSDoc comments and say that this function has an argument and it is of type string, and here's the description, and the compiler will actually read that as type information. So even if you can't, you're in a position where you maybe can't actually switch to TS files, you can still use the TypeScript compiler to check and make sure that your code kind of lines up in a type-safe way. And we already talked about the target environment, and they regularly add features and keep pace with new drafts of the JavaScript specification. So async and await were things that were added recently. I expect they will do something about some of the new stuff like private fields. As things are added to the official JavaScript spec, you'll see them added as a new target. Yes?
Do you have a recommendation for if you wanted to support, say, I think you said ES3 was like IE6.
Yep.
If you wanted to support, say, like IE11, or you didn't want to support IE at all for targets?
Good question there. So really, can I ask you to refine your question there? Are you thinking about using Babel with TypeScript? So using Babel with TypeScript, that would reduce TypeScript to really just the checker, not the thing that's producing the output. And the way I would recommend setting that up would be have TypeScript emit very, very, very modern JavaScript and let Babel take it the rest of the way. You already have something that can take regular JavaScript and target, like with using Babel preset env, you can just list your browsers, right? And say, I care about the last 2 versions of Chrome. And that library actually keeps up to date with Chrome and will, basically remove that responsibility from you and your team in terms of keeping track of what features should I enable and what not. So I would say leave your target as ES Next, maybe. Now, there are as projects get really big, sometimes there are language features that just are not appealing to include. For example, at LinkedIn, we have an app that enabling async and await would be tough, just because at every await, we have to polyfill using like Regenerator or something like that. And this starts to get expensive. It actually increases the asset size quite a bit. So I would leave all of that in the hands of linting tools and Babel. And if you're just using the compiler as a static analysis tool, leave your target set at ESNext.